everyone, my name's Jessie and I'm going to be talking to you about cosmology, specifically structure in the universe. Does it matter? So our universe is vast and it's made up of lots of different layers of things. We've got planets, asteroids, satellites, galaxies and stars. Nearby we've got our own star, the Sun, and we've got our own planets in our solar system. So this beautiful image here, which was taken by the Hubble Space Telescope, shows one of our planets, Saturn, and you can see one of its moons, Titan, just passing across its surface. When this picture was taken, Saturn was 125 billion kilometers from the Earth. And what we can see in this picture is that we've got the planets in our solar system, and in between each of those planets, empty space. If we zoom a bit further out, we find that we've got lots of these solar systems, each with their own stars and planets. And collectively, these form a galaxy. Our galaxy is the Milky Way. In between each of the solar systems in any given galaxy, empty space. If I zoom out again, to the point where we're now looking at something like this, you can see lots of these galaxies, all different shapes and sizes. Some of them have these beautiful arms spiraling outwards, some of them are elliptical. And interestingly, this galaxy here in the top left-hand corner is 7 times closer to Earth than the ones on the right-hand side. This tells you that these ones over here are ginormous for them to appear the same size. How do we know that this one's closer to Earth?
Is it because those are redder? The redshift. Is it because of the redshift? Because these are slightly redder.
Okay, I can see why you'd say that. It's actually even easier than that. You can see individual stars in this picture. So that's how we can tell. In between each of the galaxies in this picture, you've guessed it, more empty space. I'm going to do one more zooming out procedure. Last picture. Thank you. To the point where we're now looking at structures that are 600 million light years across. That's all this number means. You don't need to worry about that. And what we find when we're this far out on the universe is that we've got clusters of galaxies and superclusters. That's what each of these bright dots represents, a galaxy. And you can see that they're connected by these strands, and we call those filaments. In between each of the clusters and filaments, yep, you've guessed it, more empty space. So what do we learn from all this? Could I just have that last one available?
Oh yeah.
Right, flip it around so they can see. Thank you. What do we learn from all this? I've just shown you a series of 3 pretty pictures, all at different layers of the universe. Well, quite simply put, we learn that there are regions of space where there is stuff and regions of space where there isn't stuff. So that's how I view the cosmos. That's how you guys view the cosmos. If you're extremely lucky, if you're in London and you look out into the night sky, if you're lucky it's a clear night, you can see this perfect sheet of inky blackness interspersed with these white dots, stars. So we've got matter, then we've got empty space. So that must be how scientists also view the cosmos as well, right? Well, not quite. Scientists who study the universe are called cosmologists. And what they normally do is they assume a very smoothed out universe. So in any of these pictures we have, imagine just taking an average of that part of space where there is something, a planet, a galaxy, and the region of space next to it where there isn't anything. And you want to find a middle ground between the two, if you like. And we call this the standard model of cosmology. Cosmologists assume that the universe is the same at all points, the same in all directions, so it doesn't matter where you are or where you're looking. This is the best model we have in cosmology. It's tried and tested and it fits remarkably well with data. You're thinking to yourselves, whoa, slow down. Surely by using this model, we're just ignoring all of these beautiful structures that we've just talked about. And you'd be onto something there, you'd be quite right in thinking that. So why do cosmologists assume this very simplistic version of the universe then? Well, the whole reason they do this is because it makes life easier for themselves. The equations that you get out as a result of doing this smoothing out of the universe, they're remarkably simple. And in science, that's only ever a good thing. If you've come up with a theory that's able to explain how the world works, and it does so in a very simple way, you've done good. If you've come up with a theory that's able to explain how the world works, but it does so in quite a long, convoluted way, people really aren't sure what you're getting at, there are separate, disconnected topics that don't quite fit together, the chances are you haven't done something quite right there. So going back to cosmology then, forgot what I was going to say. The underlying maths behind it all is something you might actually have heard of. After all, maths is the language of physics, and this theory is Einstein's theory of general relativity. And his most famous equation from that, his main equation that cosmologists use, is the Einstein field equation. And that says how the shape of any region of space, how that's related to the stuff that's in it. So for cosmologists, they're studying the universe. The shape of space for them would be the entire universe, and we call that a space-time. And obviously, the stuff that's in that shape, that space-time, is everything that's in the universe. So all of these things I showed you right at the beginning. And so cosmologists equip themselves with this tool, this equation, and they use that to go and discover things about the universe. There's just one problem though, which is that in this equation, there's a special property, and it's built in because of the maths. It's fixed in, we can't change this property. And it basically says that when we do this dramatic assumption of assuming a very smoothed out universe, what it means is that it doesn't necessarily mean that we've correctly pinned down what the actual background space-time is for the universe. And what you find is that all these structures of matter, all these lumps and bumps, can actually affect how the universe behaves and affect how it changes and evolves and grows over time. And this is called the averaging problem in cosmology. And it's currently an area of hot debate. Should we start to take into account all these separate clumps of matter, or is it okay, is it good enough to assume this smoothed out universe? And so some cosmologists believe that it's time to step away from this simplistic, smoothed out universe and actually start to incorporate these lumps and bumps of matter and take their effects into account. Why? One of the main reasons for this is technology. Our technology is only ever advancing. So I'm sure you all own a mobile phone. Mobile phones these days are extremely powerful. You have the internet right there in your hand. You can connect with anyone millions of miles away, send them a photo or a video, and they can receive it within seconds. We can print things in 3 dimensions. We have cars and planes that drive themselves. We have robots that perform surgery. Technology is just always on the increase. For cosmologists, their equivalent would be the observational surveys that are about to take place in the coming years. Think of these as maps. These surveys are going to map the universe to a far greater detail than has ever been done before. And so the precision that we're able to do with these surveys is phenomenal. The theory side also needs to start pulling its weight and also needs to catch up, because the people that are working on these surveys, they're going to start getting in these enormous waves of data from these surveys, and so they need people to help them make sense of them, help them interpret the data that they're getting. So we need better and more sophisticated models to help them do this. So what do I do? Where do I come into all of this? Well, I'm a first-year PhD student, and together with the help of my supervisor, I work on making these cosmological models that have all of these lumps and bumps of matter incorporated into them. And they're toy models. What does that mean? It means they're very abstract. We're not trying to model every single particle in the universe. Instead, we're just trying to get a flavour for something called back reaction. What's that? It's just the name given to the difference between these 2 main viewpoints that I'm talking about. So assuming the universe is smoothed out, the same at all points, or assuming that it has discretized matter, separate bits of matter. And you can quantify the difference between these 2. You can get a concrete number for it, and that's called back reaction. And that's what we're trying to do. How do I do this? I use lots of maths. I use geometry, algebra, calculus, trigonometry. And I have to make sure that any model that I come up with agrees with what Einstein said. Because remember, I said that cosmologists' main tool that they equipped themselves with was the Einstein field equation. I have to make sure that what I'm doing agrees with what's predicted by his equation. The equation's fixed, I'm not trying to change what he said. And once I think I've got a model, you find that it can be described by a single equation. We call that a metric. And because that's an equation, I can plot it. Because this is a universe, I can 3D print it. And that's exactly what I did do. So this is a 3D printout of one of my cosmological models. This is a universe that contains 64 separate bits of matter. And you might be thinking to yourself, 64, that's nothing. This picture here probably has billions, just like where my fingertip is. Billions of stars. Well, the thing is that I can make these models with any number of bits of matter that I want in them. I can make some with just a handful of bits of matter, or some with hundreds or thousands. What's this physically going to correspond to or represent? If I've got a universe that I've made with just a handful of things in, that corresponds to the very first picture I showed you. So when we're looking at things nearby, just a handful of planets in our solar system, when we zoom out, that would then correspond to one of my models with hundreds or thousands of bits of matter in. So looking at a galaxy, for example. What do I do once I've got my model? I compare it. I compare it to what the same model would look like, but had I assumed this very smoothed out universe. So had I used the standard model of cosmology that I talked about near the beginning. What am I comparing? I can compare anything I like in these two models. For example, a physical distance. So I can take a physical distance from A to B in this smoothed out universe, and a physical distance A to B in my clumpy universe. If I get the same answer, there's no difference between either of these two viewpoints. So there is no back reaction. If there is a difference, then that would suggest that's evidence towards having to relax these rigid assumptions from the standard model, and perhaps we should start to take into account these clumps of matter. So is this what we found? Yes, in a roundabout way. So we found that when you have a universe with hundreds or thousands of separate points of matter, the difference between the two distances from either of these two viewpoints is negligible. When you have a universe with just a handful of bits of matter, there is quite a significant difference. So because I'm only a first year PhD student, my job is to do more of this, to keep building models that have even more complicated, different configurations of matter, and to even add more exotic things, something called a cosmological constant, which some cosmologists believe is actually dark energy and is responsible for some of the strange things that we've been observing as of late. So recently we've been seeing how everything in the universe appears to be moving away from everything else, as if pushed by an invisible force. So you might be thinking to yourselves, that all sounds really cool, well and good, but what does that actually have to do with me, a single individual here on Earth? Well, I'm just going to leave you with this one idea. I'm sort of coming to the end of what I wanted to discuss with you today. And the idea is that 150 years ago, a very famous, clever physicist called Maxwell, and he wrote down 4 very beautiful equations that describe electricity and magnetism. These were also very abstract, very mathematical. Do you think, at the time, he could possibly have imagined that 150 years later, we would all be using the very same physics that he came up with when we plug in our phones to charge them, or when we turn on the television and radio? Of course not. So, it's by its very nature that theoretical physics, the physics that I do, physics that Maxwell did, it doesn't have any immediate or direct applications to everyday life. It's not all doom and gloom, because what it does do is it opens doors. It opens doors for engineers, for chemists, even for medicine. And so theoretical physics is very important towards our understanding of how the world works. And the work that I'm doing is just very small baby steps towards this understanding. Thank you. Does anyone have any questions? Yeah.
How is the new discovery of gravitational waves going to influence your is it going to happen in the universe? Because I'd imagine that you could use gravitational waves to stop more structure in the universe. Am I right?
It doesn't have. So a question was about gravitational waves and does that affect my research? Very good question. And the work that I'm doing, it's not going to be influenced by gravitational waves because the universes that I look at are static, so they're at a fixed point in time. So if I was to then go and evolve those in time, perhaps they would need to be taken into account, waves.